Hey Google, Dhruv here, and in this video I'm going to talk about the last half of my project from the test setup beyond all the way through to the end. Now I know what you might be thinking. You might be thinking, Dhruv, the data is supposed to go in the data section. This is the conclusion section. What are you doing? Well, in this video I'm going to talk about it all. So I'm going to start with a brief review of what we just talked about, from the problem statement through the development, and then I'm going to talk about the data I collected from the test setup which I designed, and then I'm going to finish off with an awesome discussion about the conclusions I drew from this research and where this project can go in the future and what I can do to expand my research beyond what I had originally thought. So let's go back a little bit, and if you remember, the problem I'm trying to tackle is that quadriplegics cannot use their computer, or cannot use the keyboard or mouse, and hence cannot play computer games. And so to tackle that issue, I created a face tracking keyboard and an eye tracking mouse. So when we left off, I had just started with, I just described my test setup for testing the accuracy and speed for the keyboard and the mouse. So now let's go on to see the results of that. Now it's important to remember that the results are coming in two different sets. The first is coming from qualitative analysis and the second is coming from quantitative analysis. What you see on the screen right here, this is quantitative analysis. This is coming straight from, this is the accuracy and speed data for both of the devices. Now the qualitative analysis comes in the usability, which you can see again in this video. I've included the demo video where I'm using the device to play the game Portal, and from there, once I was able to play the game Portal through a couple levels, I decided, well, this is actually a usable device. I wouldn't mind using this device in place of my regular keyboard and mouse, and so that's what the qualitative results show, that the device basically it works. But qualitative analysis on its own is not a really good measurement of success, and that's why I've included this quantitative data. So let's start off with the accuracy and speed, which are part of the usability criteria. And so if we look at this big table here, it looks kind of intimidating, but here's the gist of it. Over here on the far left, we see the subject. Now, I wanted to make sure that I test this device under conditions of use, and people have different faces. No two faces are exactly the same, so I wanted to make sure that I tested this device under its conditions of use. So I have a variety of genders, facial structures, and age groups here. So you can see I have a boy with a wide face, a woman with a narrow face, a boy with a narrow face, and a man with a wide face. So I have three age groups, young and old, boys and man/woman, and then I have two different facial types, narrow and wide, and then I also have two different genders, boy and girl. So I have various different, I've tested on various different facial structures, and we can go through now and see what that result was. And what I found was it really doesn't matter what the conditions of use or what the person's face looks like. If the device is properly trained, then the accuracy still remains remarkably high. If we go all the way to the far right and look at the keyboard accuracy, you see that this is actually identified a number correct out of 30. So you can see they got 30 out of 30 correct, 30 out of 30, 100% accuracy, a little bit lower over here for this person's face, but still across the board, really just very, very high accuracy, 30s on all of these, 100% accuracy. Now you may notice in here, you might see, examples like this, where there seems to be no data here. Now, what that means is that the accuracy was too low, it was such an outlier. That data is not acceptable. That is a limitation of the study, that some of these points just weren't being tracked. And that was because the action associated with this command was not, it did not end up being usable for that person's face. It did not end up being, it was not as easily recognized by the Kinect as I thought it would. So as a practical matter, I would actually have to replace all of these starred commands with a different kind of action. So I might replace this one. So this one, for example, was, I don't know, let's say that this was sliding to the left or something like that. Then this would be replaced. So as a practical matter, I would not use that action as a command, so I would have to replace this. So that's why this data cannot really be included in the rest of the study, because it's such an outlier, it's such an anomaly in the data. because aside from that, the device exhibits very high accuracy. It's not a good representation of the data. So if we compare these values to back here in the discovery data, you see that the correlation between the yellow and the blue values are pretty good indicators of the accuracy. We'll see when we see high differences between the values, then we see high accuracy as well. So this seems to be a pretty good indicator of how well the device will perform later on in the accuracy. So it's sort of like a validation of my methods. So if we look at the mouse speed and the face tracking speed, we see that they're still quite fast. Very low differences between the face tracking and we see a very low difference between the face tracking speed and the keyboard speed, as well as between the eye tracking mouse speed and the regular tactile mouse. So basically what we can gather from this slide is that the face tracking device exhibits very, very high accuracy. The only reason that it wouldn't exhibit high accuracy is because if the action associated with that command is not acceptable, and then speed, eye tracking, and mouse and face tracking keyboard are very comparable to their mouse and keyboard analogs. So now some conclusions that I can draw from this study. First, technology that is aimed at quadruped's muscle line and muscles above the neck. That is going back to the user demographic, user design constraints, which I identified way early on in the study. Now, a large number of games we can classify into point of view and single point input games, and this was very important because it allowed me to identify a set of success criteria. So current devices on the market today do not meet the functionality, usability, and cost needs of the demographic. If you saw the last video, you'll know that the devices in the market cost too much and they don't have the right functionality necessary. They're not solutions to this problem. So a natural user interface that can recognize facial gestures and eyeball movements works, and I can develop it using commercially available technology. So I never really mentioned cost in the data section, but that's where the commercially available technology means. This device, in general, all in all, will cost around $300, and that's because the Kinect costs $200, and the eye tracking device costs $100, gives a $300 total cost. The code, the application that I wrote, which integrates these two together, would be available as a free application, thus minimizing the cost. Most of the work for this project was really done in the software phase, so that's why I'm able to keep the code open source and make it as a free application, reducing the cost significantly. So a successful keyboard prototype I was able to develop. It exhibited near 100% accuracy, except for those instances where the data, except for those anomalous instances. And I conducted a fair number of trials. I conducted about 240 trials, 8 commands for 30 times each. So I built a successful mouse simulator using the eye tracking device. It was adequate for game playing. The accuracy was enough that I was able to, was low enough. This 344 pixel average error was still low enough that, because that was just only occasionally is that accuracy become a problem. Most of the time the error is very small, only about 5 to 10 pixels. So now the neural network was really the heart and soul of this project. It enabled the recognition of different variations of the same facial gesture, and that allowed for the consistency that we see among this data. If we look back here and we see that no matter the facial structure, the user still has super high accuracy, and that can be attributed solely to the neural network. It's able to take in the fact that people have different facial structures and still recognize the commands with high degrees of accuracy. So now let's move into what can I do with this research in the future. Well, we can classify everyday actions as unimodal or multimodal, and this comes from the study of human-computer interaction. So multimodal actions require multiple input channels. Unimodal actions require one input channel. Now, at its core, this interface recognizes facial gestures and eyeball movements and converts them into commands. So this interface can be used for more than just gaming. With a simple change of a few lines of code, I can make this interface do any multimodal action. This includes other computer applications like surfing the internet or writing documents. It also includes things like driving a car as well, because that is a multimodal action. However, gaming provides a safe way to test the interface before I crash my car. So the now let's talk about how I expand this project. First is new device customization options. Looking at different animation units. We're looking at different ways to select those animation units and possibly adding some more animation units in. Adding more commands. Obviously, this is going back to just increasing that functionality, making the device more applicable to other fields of a person's life other than just computer gaming. And then some sort of next command prediction. That's actually that goes along with the increasing the functionality. Next command prediction to speed up gameplay, as well as some sort of next word prediction, so that way I can enable typing in the device as well. So in summary, just going through the background of the whole project, I recognize this problem of quadriplegics not able to use the computer, and devices that are targeted at solving this issue are not adequate. So I looked at several alternatives to solve the problem: wearable devices versus natural user interfaces, different kinds of natural user interfaces. I settled on building a face tracking keyboard and an eye tracking mouse. I tested the device under different conditions of use for different users with these are tested on actual human subjects, all of them with different facial structures. I determined my possible uses for the device, as well as some areas for expansion for the device as well. So with that, I'd like to conclude this fairly short video on the conclusion, and that's on the conclusions and the data from this project. So thank you very much, and let's head on over to the acknowledgement section. Thank you very much.